let us begin by asking the question, what is cosmology? So, can you guys write down what do you understand about cosmology in the chat box? Just a few ideas about what is cosmology, what do you think cosmology is? Or you can just unmute yourself and say.
Study of the universe. The study and expanding universe.
Sir, cosmology is a branch of physics or metaphysics.
Okay,
Sir, I think it is used to study an expanding universe.
okay. So, in order to understand what is cosmology, we must first understand what is this universe about. How do we um, observe this universe? What are the intricacies of looking at into the universe, etc. Okay, so we'll
So,
begin by looking at the night sky.
so
Okay.
I think, may I answer that what is cosmology?
Yeah, sure.
I think cosmology is the field of science in which discusses about space and about universe.
Yes. So cosmology is the study of the universe as a whole. So in order to understand cosmology, we must start looking into the sky. So when we look into the sky, what we see? Well, if we are living in a city, you are facing a lot of light pollution, and when the weather is not comfortable, there is so much of cloud, and you can't possibly see anything. Even the moon itself is very hard to see in this picture, right? So this is our day-to-day life, and we are trying to get a picture out of the sky. And if you are living in a metropolitan city or a city with a lot of light pollution and other kinds of pollution, it's very hard to understand what is going out there. Okay, so it is very important that we must understand how we are going to observe the universe in order to have a better grasp of what is cosmology all about. Okay, so let us see a video right now. This is going to be a 3-minute video. It is about the light pollution and all thing. Okay. So this is a cityscape and it is getting night, and we can see how the city glows up, and we can't possibly see anything in the night sky.
Sir, Sir, what is light pollution?
Okay, so the light pollution is that if there is too much light in the city, we can't see anything in the sky. We will understand that much better after watching this video. Okay, so let us
Okay,
watch
sir.
this video first and then we
Okay,
can
sir.
discuss. So what you see right now is the night sky, and sun goes down, and this is the pollution level 6. That means it's a slightly higher pollution. But if the pollution is very, very less, if the pollution level is relatively low, we can see a much more detailed sky. Like, for example, now in the
Happy
video, you
birthday.
can see the galaxy itself, our Milky Way galaxy. The reason why we can see the Milky Way galaxy is that because the light pollution is very low. Okay. So we are trying to observe our universe from our planet Earth.
No,
It's very difficult to go.
where is that uh, lighthouse that was shown in CA? It was shown.
Hello, can you mute your audio? If you have a
पैरेंट बुला रहे
question,
वहां से
you can
बटन
unmute
डाले
and
था
ask.
भाग
Otherwise,
जा वहां
please
से
mute your audios. Okay. So what you see right now is if the light pollution is very close to zero, that means there is no light pollution at all, we can see a very clear sky and we can see the details of the sky. Okay.
Sir,
So this is what this video is all about.
sir,
Yes.
Hmm?
what is the light pollution level in India?
A light pollution level in India depends on where you're from. For example, if you're living in a city,
जल्दी
the
करो
light pollution level can go up to 8 or 9. If you're living in a countryside, if you're living in the regions of mountains, like for example in the Himalayas, the light pollution level can go down to 2 or 3. Okay, for
Okay,
example,
Okay.
if you are staying in Ladakh or Jammu and Kashmir, such remote areas, the light pollution level is very low. But if you are living in Delhi or Mumbai or any metro cities like Chennai, then the light pollution level is quite high, and it is very difficult to see the night
I
sky.
have a question.
Excuse me, sir. Sir,
Yes.
sir, I couldn't understand anything because everyone is unmuted and I can't hear your voice even.
Is that the case with everyone? Can
Sir, I just joined.
Yes,
Can
sir.
I
I
have
yes,
cannot
a
sir.
hear
comment?
you. Sir, I
We are
cannot
doing.
hear you, sir.
Sir, everyone is
Some people are
unmuted.
unmuting. Mobile only.
so can nobody hear me?
Sir, only Divyanshu
Sir,
Suryavansham is unmuted.
sir, someone keep on talking, sir.
Sir, it is very disturbing.
Thought everyone can hear me. Hello.
No, sir, we are not able to hear you.
Okay, 1 second. Let me check my audio, and I'll be right back.
Sir,
Sir, what about your
Can you hear
audio?
me right now?
So
we
it's not about your
Sir, we
audio.
cannot hear you.
Sir, in this meeting, everyone is unmuted, so I can't hear it any more clear.
sir, only Divyanshu Suryavansham is unmuted. Everyone is muted. I checked the participant spot.
Okay, can you hear me right now? Just drop in a comment.
Okay, yeah. Sir,
Yes,
can
sir.
I share?
Yes, I think you can hear me. So
Sir,
there is no problem with the audios. Let me share the screen again.
sir, I just joined. So can I have a follow up on what we are doing?
Yeah, sure. So we are discussing about the universe, and before we discuss about the universe, we must first understand how to observe it. So we started with the basic light pollutions, because if you are trying to look at the universe, you are essentially trying to look into the skies and see what is out there. Okay, but if you're living in a cityscape like this, you can't possibly see anything with the clouds, and even with this much uh, clouds, you can't even possibly see the moon. So if you're living in a city, you're very unlikely to see any good sky. So this is a video about the different kinds and different levels of light pollution. So as you can see in this video, let us see the video in complete. So a city is going towards its night time, and you can see the city brightens up, and you can't possibly see anything in the sky. So this is a light pollution level 9. So whenever we have a light pollution level close to 9, you can't possibly see anything. So you can look in the sky, you can see some flights going around, but you can't possibly see anything in detail. You can maybe see some stars or even moon, but other than that, you can't see anything. But if the light pollution level is very low, you can't actually see many things. You start seeing Andromeda, you start seeing our own Milky Way galaxy. What you're seeing right now is the Milky Way galaxy. So when the light pollution level is very low, you start seeing much better sky. Okay, so that is the basic idea of observational cosmology. Or this is something you might have already seen in astronomy classes or classes related to telescopes and everything. So a perfect sky is very important when you're trying to look into the sky. Okay, so this is very close to any Himalayan regions. For example, if you're in Ladakh or in places like Nainital, you can see very clear sky, and the light pollution level can be very, very low. Okay,
Sir,
so this is
I have a
all
question.
about looking into the sky. So when we look into the sky,
I have a
there are
question.
different levels of light pollution. We can see if the light pollution level is 1, means an excellent sky. We can see the very details. And as you can see, when we progress towards much more polluted area like a city sky, we can't possibly see anything, right? So this is the same place, but different light pollution level gradient as it move from the right to left. So it is very important to have a very clear sky in order to understand this universe. But just having a good sky doesn't mean that we completely understand the universe. We need to find out how the universe is trying to work. So that is what essentially cosmologists are trying to do. They are trying to understand the origin, the evolution, and the dynamics, and maybe possibly the fate of the universe. Okay, so in order to do that, we
Sir,
need to, yes.
sir, how does light pollution affect our night skies?
So what is light pollution? So when there is too much light in the city, it scatters off from the atmosphere. And because of that, we can't see anything outside. Okay, we can't see the stars, we can't see the nebula, we can't see anything. Okay, so that is one problem. Light pollution is not going to affect our health. Okay, it is not like unlike other pollution. Like for example, if you are having air pollution around you, you can't probably breathe well. But with light pollution, you are probably safe. But when it comes to cosmology or astrophysics or astronomy in general, light pollution is a very hectic pollution. Okay,
So
so
why does the sky revolves in the light pollution level of 1, 2, or 3? The sky
so
revolves.
it is not like sky is revolving. Sky is always going from east to west. That is something that uh, we will discuss in the next few slides. Okay.
So it's
So
because of the Earth rotating.
yes, it is because of the Earth is rotating. Everything in the sky tends to move from the east to west. So that is a phenomena because the Earth is rotating. But we will come to those points in a bit. Okay, so when we look into the sky, we see several different things. Okay, first and foremost, we see our moon. Then occasionally we see different planets. And if you are lucky, we see comets. And if you have a very good telescopes or binocular, we tend to see something like nebula. Okay, so there are several different things in our sky, mostly in the night sky. In the day sky, we generally don't see anything other than our sun because sunlight scatters off from our atmosphere, and most of the time we can't see anything more than our sun itself. Okay, and occasionally sometime we can see moon in the day sky, but we can't see any stars in the day sky. So in order to observe, we need as much less light as possible. Okay, so that is one thing about observations. So when we look into the skies, we see that everything is going around the Earth. So that is what we see in the first video, right? The entire galaxy is armed. The Milky Way galaxy is moving. The stars are moving. Everything is moving from one direction to the other. And it feels like the Earth is quite stable there. Okay, and based on these observations, people started making a model of our universe. Okay, and people thought that the Earth was the center of the universe, and everything goes around the Earth. So that is the first model of our universe. Okay, and this is perhaps the first cosmological model, but the term cosmology was not very well established during those days. Even the idea of astronomy or astrophysics, those subtle differences were not there. They were simply looking into the sky and trying to understand what is going. So the very basic
Sir,
understanding that we get is that the Earth is very stable
sir,
and everything is going around. That is what we can see. So let us go back to this video and see this video again, maybe around from this point onwards. Okay, what we see is that it feels like the Earth is stable and the entire sky is going around. Someone already asked that question already, right? So this is what we see. And occasionally we see something going here and there. Maybe we can think of those things as transient events. But in general, the entire sky seems to go from one direction to the other. So that is what we see in general, irrespective of the location from we look. Okay, whether you're looking from India or whether you're looking from China or any other place on the earth, this is what we are going to see. Okay, the entire sky tends to go from one direction to the other. Okay, so people thought that Earth is at the center of the universe and this entire universe is going around the Earth, and we had no idea about these tiny, tiny details of the stars. It looks like these stars are fixed on the particular screen, okay, as if it is fixed. Now we know that stars are not fixed, the entire universe is much bigger than we anticipated. But from this picture itself, we can't make that out. Okay, we can't really say that the stars are moving in different directions. It feels like everything is moving together. Okay, and that is the reason behind the first model of our universe, which is the geocentric model or the Ptolemaic model, where the Earth is at the center and everything is going around Earth. Okay, this was a very well established picture of the universe for at least a few hundred years. But then people started having discussions about, okay, but when we look at the orbit of Venus or Mercury, it feels like it is not just going around the Earth. Okay, sometimes it goes from one point to another and then comes back. Okay, for example, in this diagram, you can see that it goes to point number 2 and then goes to point number 3 and then again goes back to point number 4. Okay, so from two, so in general, from 1 to 2, it is going in one direction. Then from 2 to 3, it goes back, and then from 3 to 4, it going in the same direction as earlier. So it's sometimes some planets, especially Mercury and Venus, tends to show this kind of motion. And this motion is sometimes also called as the retrograde motion. This is not up to scale. This is just a schematic representation. So people started constructing complicated orbits in order to explain this. So for example, this
Sir,
center dot, yes,
sorry, look at my new background.
sorry.
Sir, look at my new background here.
Please do not interrupt the class unless you have a question regarding the class.
Excuse me, sir.
We can have fun discussion at the end of this session because this is for your ISO exam. So please pay attention. Okay.
Okay, sir.
Okay. So don't worry, we can discuss about fun facts at the end of the class. So this is one model of the universe we started with. So we thought that Earth was at the center and everything is going around in circular motion. That is what we thought. And then we see the orbits of Mercury and Venus showing a different kind of motion. Like, for example, it started from location 1, and then it goes to location number 2, and then goes to location number 3, and then goes to location number 4, and so on. So it kind of goes around the orbit like a multiple orbits are there, like, and that is technically called as epicycles. Okay, so epicycles is additional orbital cycles around one particular orbit. So people thought that this is the case, and they decided to construct more complicated model out of this. And this is what that complicated model would look like. Okay, so this is the geocentric theory of universe, in which Earth is at the center and every planet goes around Earth in much more complicated orbit. So can you imagine solving equations for this orbit? It's very difficult. Okay, so it becomes very complicated. But then a few thousand years later, people realize that this may not be the case. What if Earth is not the center? What if the sun was the center? Okay, instead of epicycle, people created a much better model, which is sometimes called as the heliocentric theory of universe. Okay, in the heliocentric theory, which is credited to Nicholas Copernicus, or Copernicus model of universe, the sun is at the very center and everything goes around it. So Mercury goes around first, then comes Venus, then obviously our Earth is there, and then the moon is around the Earth. So people already understood that there are planets and planets have satellites and sun is at the center. Okay. It turns out that this is not the model of the universe. This is the model of our solar system. But people were not they didn't had sophisticated instruments or anything to explore the universe as a whole at that moment. But with the limited data they got, sorry, uh, they from this complicated picture of geocentric model where there is orbits and orbits over orbits, which is called as the epicycles, we came to a model which is much more simpler, but it explains almost every observation that we see. The retrograde motion of the Mercury and Venus is now replaced. Okay, so there is no such motions. Everything is going around Sun. So this was the idea of the entire universe at that point. People thought that this is the universe that we live in. Okay, and every stars and every other things that we see in the night sky is at the very edge of the universe, and it is embedded there, and we don't know what they are. Okay, that was the idea back in the time of 1500s and so. Okay, it is very uh, even before Galileo and Newton. So this is the observations, and based on these observations, people first started with a geocentric model, and then they evolved into something called as a heliocentric model. Okay. So in the heliocentric model, again, there are several assumptions going in. The sun is at the center. Then there is Mercury, Venus, Earth, Mars, everything is there. And people thought that the orbits of all these planets are circular. Okay. So there is no reason to assume that, but people thought that circle is a very perfect geometrical object. And perhaps that is a better way to look at the universe. Okay, so they even got this kinds of orbits for dwarf planets like Ceres and everything. So they constructed this model, but there was a slight imperfection, and that imperfection can be accounted with something called as conic sections. So if you take a cone, for example, like your ice cream cone or anything, if you cut it perpendicular to the base, you will get circle. But if you cut it slightly inclined to the plane, you will get an ellipse. But if you cut it at a 40 parallel to one of the edges, you will get a parabola. And if you cut it perpendicular to the plane, you will get a hyperbola. It turns out that most of the orbits of the planets around the sun does follows this elliptical orbit rather than the circular orbit, because circular orbits are very rare and it is very critical. It's kind of unstable. A small perturbation can kick you out of the circular orbit. But elliptical orbits are much more stable orbits, and they will remain as such for a very long period of time. But when the eccentricity increases, it becomes close to a parabolic orbit. And parabolic orbits are the orbits traced by most of the comets in our night sky. Okay, so comets are visitors to our solar system. Comets doesn't necessarily live inside the solar system. They are either from the Oort cloud or from the Kuiper belt. Occasionally, due to some perturbations or some actions at that level, they tends to come into the gravity of the sun, and then it goes around. And those orbits are usually parabolic orbits. Okay, but for the orbits of the planets and almost every satellites in our solar system, they are in elliptical orbits. Okay, but sometimes these elliptical orbit can be too big. They orbit might interfere with other orbits and all. For in the case of Pluto, when I was your age, I used to study that Pluto was a planet, but right now Pluto is now taken as a planet. Why? Because planets are those things which kind of goes around the sun. But the orbit of Pluto is much more complicated, and it tends to share orbit with other planets as well. So it is too tedious to understand Pluto as a planet. So that is why Pluto is no longer a planet. Anyway, in most of the cases, the planets will have an elliptical orbit, and in the case of comets and long time visitors, it might have a parabolic orbit. Some of the comets does have a hyperbolic orbit. So what is the problem with parabolic and hyperbolic orbits? These kinds of visitors comes in one and goes out forever. They do not come back. But in the case of elliptical orbit, they tends to come back. So in the case of our solar system, Sun is at the center and Mercury, Venus, everything is going around and it stays there. Okay, no one is going out of the solar system. But for example, a comet, it if it has a parabolic orbit, it will come inside and goes outside. So these kinds of understanding gave a much more bigger perspective of what we are looking into. Okay, then yes, Dia, you have a question?
Then what about the Halley's Comet? It comes after every
Yes,
7
very good question. So Halley's Comet does have an elliptical orbit. Okay, not all comets have parabolic orbit. Most of the objects in the solar system has an elliptical orbit and it goes around the sun in regular interval. In the case of the Halley's Comet, it has a very long um, orbital period, which means it goes around the sun once in every 87 years or so. I don't exactly remember the number, but it takes a very long time for the Halley's Comet to come by. So it has a very long elliptical orbit. Yes, Ian, you have a question?
So, what can you give an example for a planet which is having a orbit of hyperbola?
Uh, Planets doesn't have a hyperbolic orbit. For example, in order to be called as a planet, it should go around the star in a periodic motion. For example, Earth goes around Sun in once in every 1 year, right? It takes 1 year for that is how we define 1 year. But
Yes.
in the case of, let's say, Jupiter or Saturn, it takes more than 10 years. It takes 14 years or 12 years, depending on whether you're talking about Jupiter or Saturn. So it takes more and more time, but the time that takes is the same. Okay. For one orbit, if it takes 12 years, the other orbit also takes 12 years. That means it always comes back. But in the case of parabolic and hyperbolic orbit, they just come in and goes out. Okay. It is not a closed orbit. Okay.
Okay, sir. Okay, sir. Thank you, sir.
Okay. I'm just calling out names based on what I'm seeing. Advika Singh, you have a question?
Explain the epicycles. I did not understand that.
Okay. So let me go back to that slide. So even before we understood that Earth is not the sender, people thought that Earth was the sender. But if you take Earth as a sender and everything going around in circular orbit, that cannot explain the motion of Venus and Mercury. So they constructed multiple orbits. So instead of this one big orbit, people thought that, sorry, instead of this one big circle as the orbit, people thought that, okay, it is going in a very complicated path like this springy motion. So an orbit over an orbit, there is a smaller orbit here. You can see that, right? So these orbits are sometimes called as epicycles. Not sometimes, usually called as epicycles.
Okay,
Okay?
sir. Thank you, sir.
Okay. Let us continue with the talk, and if you have questions, we can discuss later. I think we have a lot of things to discuss. Okay, so this is all about the orbits, and based on the orbit, people had a much better understanding. And that is when Kepler comes into the picture. Okay, what Kepler did is that he devised three planetary laws, okay, which was then later proved by Newton using his Newtonian mechanics. Okay, so in order to understand cosmology or in order to understand the basics of astronomy or astrophysics, you must pay very good attention to your mathematics classes as well as your physics classes. Okay, so in your school curriculum, you already study physics, mathematics, chemistry, biology, and everything. But if you want to be an astrophysicist, you must pay more attention to mathematics as well as physics. Okay, so that is where we are going with this. So the Kepler's laws of planetary motion says that instead of circular orbit, planets goes around a star in elliptical orbit. Okay, the sun is at one of the foci of this ellipse. Ellipse has two focus. We call them foci. And the sun is at one of the foci, and the planet goes in the elliptical orbit. Okay. So that is the first Kepler's law. The orbits are ellipses.
Sir,
Then there is an idea of equal area, equal time. Okay, so when the Earth is closer to the sun, it kind of moves much more faster.
sir,
And when it is very far away, it kind of moves much slower. Okay, that means equal area in equal time. So what is the area we are talking about? We are talking about the area in this sector. Okay, so if you connect these dots together, the sun is at one point, the planet starts from here, then the planet goes to another point, and if you cover this shaded region, and if you come here, again the planet starts from here and goes here. The number 6 months is arbitrary, you don't have to pay attention to that. This area will be same as the other area. So this is the second Kepler's law. And the final Kepler's law is that the time taken for this orbit, like for example, Earth takes how many years? Just 1 year. That is how we define 1 year. So Earth goes around this orbit in 1 year. And from that, we can calculate the semi-major axis, the length of the semi-major axis. And if you cube that number, that will be proportional to the period square. T is the period of the orbit. By period of the orbit, I mean the time taken for the planet to go around the star in one time.
Sir, I
Okay,
have
just
two
one
questions.
single orbit is the time taken is called one period. Okay, and if you square the period, that will be proportional to the cube of the semi-major axis. So these are the Kepler's laws of planetary motion. So we started with the geocentric model. Our Earth was a center, and then we had orbits. And then in order to explain some orbits, we tend to use complicated orbits such as epicycles. But all the complications was removed once we used the heliocentric model, where sun is at the center and everything goes around the sun. Okay, everything was quite simple and explainable. But then there was another problem. The problem was everything, we assume that everything goes around in circular orbit, but that is not the case. People realize that it is not going in circular orbits, it is going in a much more detailed orbit called as the elliptical orbit. And we understood that there are these circular orbit, elliptical orbit, parabolic orbit, or hyperbolic orbit. They are all part of one conic section. So conic section is a section or a topic that is discussed in mathematics classes. So if you pay attention to your maths classes, you will eventually learn these. Usually these are high school level topics, but it is better to see these things earlier so that you will understand them much better. Okay, so based
So,
on these, yes,
yeah, can I ask one question?
yes.
Sir, you taught us about this orbit, the elliptical orbits. I just wanted to know how the Alpha Centauri orbits. I don't think they orbit in ellipses, right?
So elliptical orbit is still an approximation. This is when only there are two or objects in our consideration. We will discuss about a much more complicated orbit as we move further. Okay,
Yeah, because
if
Alpha Centauri,
it is almost an elliptical orbit, but not a perfectly elliptical orbit. The ellipse itself is shifting. Okay,
yeah,
we will come to those complicated orbits later.
okay.
Okay. Kaushiki Das, you have raised your hand. You have a question?
Yes, sir. Sir, I wanted to ask that what is semi-major axis in the third Kepler's law of planetary motion?
Very good question. So here in the ellipse, we can see two axes. One axis is much longer and the other smaller axis is also there. Okay. Is that clear?
No, sir. I was talking about third Kepler's law of planetary motion.
Yeah,
What is
I'm
semi-major
coming to
axis?
that. In the third image, you can see two perpendicular lines. Okay, one is a very longer one and the other is a smaller one.
Yes, sir.
Okay.
Yes, sir.
So the bigger one, the bigger length scale, that is called the major axis, and the smaller length scale is called the minor axis.
Okay, sir.
Okay. And semi-major means the half of the major axis.
Okay, sir.
Okay. So the length A. So in the case of circle, there is only one kind of axis. All the distance from the center is the same. But in the case of ellipse, if you take a center, the distance from the center to that ellipse is not same. Okay. For example, in the line of where the sun is kept, that is a much longer line. But that line where B is indicated, this is a much smaller line. So this axis is called as a minor axis, and this axis is called as the major axis. And
Okay,
A is the half of the major axis. That is why we call it semi-major axis. Okay, semi
okay, sir.
just implies that half of it.
Okay, sir. Thank you, sir.
Okay.
Yes, sir.
Okay.
So,
Vihan
does it,
Rajput, you have a question?
sir, I learned that sun also revolves around something. So what does the sun revolve around?
Oh, very good question. So we will be going into the details of that. So right now we haven't seen anything complicated in the universe. We just looked into the sky and we are only trying to understand what the universe looks like for us. Okay. So let us move on with the presentation. So here is another video. Okay.
Sir, you said, as you said, from the center, the ellipse has different like measurements, right? Different legs.
Sorry, can you repeat your question?
So, as you said, the ellipse from the center point, it has different lengths to its sides, right?
Yes.
Such as major axis. So as I learned, I think an ellipse has two focus points, right? Not a center.
Yes.
So, how did it get a center?
Okay. So by center means the midpoint between the two focus.
Okay, and I've learned one more thing. Any type of wave, any type of ray, if it's an enclosed thing inside of a ellipse, then if any wave is getting transmitted through one focus point, after at end it will only reach focus point number 2, right?
I didn't quite understand your question. Can you
Like
repeat your question?
if a person is in an
Okay.
enclosed room, which is a shape of an ellipse basically.
Okay.
So then, yeah, which is a shape of an ellipse, and the two focus points are marked on the ground.
Okay.
So if two people are standing there, the slightest amount of sound, even if you're standing meters away, not meters, even if you're standing kilometers away, the other person will always hear because it will always be reflected to the second focus point, right?
Yes, exactly. That is true. Let me try to share a different screen. Let me see if that is possible. Okay, now you can see my screen, right? Let me try to draw something. So if you take an ellipse, for example, and sun is at one point, and this is a focus point. Let me try to draw that differently so that it is much better.
So you're
Okay.
saying the sun is at the focus point around the ellipse which Earth is orbiting at.
Yes.
Okay, so
So that is
so
our Earth,
basically,
and
okay.
this is the major axis, and this is the minor axis. Okay, and this line is what we call as D, and this line is what we call as A, and A is the semi-major axis. And where is our sun? Sun is at the focus. So the focus, there are two focus point. We call them foci. Now the question someone asked was that if someone is standing here, they tend to say something and the sound wave goes straight and it reflects and come back to the other point. So this is always true. So no matter where you speak, it will always goes back to that point. So this is how ellipses are formed. So this is the basic idea of ellipse. Okay.
Sir, you're echoing.
Yeah. Oh, okay.
Sir, excuse me, sir.
Yes.
So, sir, how does this property means how does the property apply for the sun? Is it for the light that if the light of the sun is coming from anywhere, if
No,
the
no,
sun
no,
is
no,
at
no, no. This has nothing to do with the sun. I'm just stating a property of the ellipse itself.
Okay, sir.
Okay.
Which means, sir, it means one more thing. It means one more thing, that if if the sun is transmitting light rays to all the sides, right, 360 degrees, all the sides. So if Earth is rotating in an exact ellipse, and if the sun is at focus point 1, then if light rays hit Earth and are reflected back, they always reach focus point 2.
Yes.
Okay.
But that is not the point that I'm trying to make here. Okay, this is the construction of an ellipse. For example, if you take a circle, for instance, so if you have a circle, it only has one kind of axis, the major axis or the minor axis. And if you take this length, and this length will always
It's
be the radius of the circle. If this is a circle, both will be the same. Okay.
okay.
So if this is the radius of the circle, this will also be the radius of the circle.
Okay.
Okay, so this is radius and this is radius. But in the case of ellipse, those lengths are different. One is A and the other is B. B is less than A. So this is the difference between a circular orbit and an elliptical orbit.
Okay,
Okay.
so one more thing, an ellipse, when it's constructed. So, if we construct ellipse out of nothing, so if we just take a circle and elongate it, then we can't construct an ellipse, right? We can't be sure.
Why?
Because we don't know if we are constructing an ellipse that has two focus points at equal length, right?
Yeah, this is an ideal case. Most of the orbits are very close to ellipse. That is something what we understand from observation. Okay, one thing that you need to understand right now is that when we talk about cosmology or understanding about the universe, we are trying to make these observations and trying to understand what these observations means. Okay.
Yes, sir.
Okay. Okay, very good. So let me continue with the syllabus topic, that is the expansion of the universe. So let us pay attention to this video. So the expansion of the universe is considered as one of the most important observation of the last century. And if you look into the details of it, we will see that these galaxies are going further and further away. Okay. So this is the construction of a celestial sphere. And if we embed these galaxies in the celestial sphere, we see that these galaxies are moving further and further away. But we can also picture this as the universe itself is expanding, not like the galaxies are simply moving away. Okay, that is one way of looking at it. But when we take a much more detailed picture of the universe, so this is us, this is where we are located. And from this point, if we started looking much longer distances, we will see
That's the
that
observable
there are
universe.
many other structures in this universe. Okay, so this is from a survey from 1998. It's a very old survey. But based on these ideas, when people started looking at much further objects, like in the scales of megaparsecs and kiloparsecs or megaparsecs range, we see that these things are going faster and faster away from us. Okay. Do you know who made this figure on the first place?
Sir, can you repeat the question?
So,
So
was
are
it
you familiar
Edwin
with this diagram? This is an image, it's a very famous image plotted by a very famous scientist.
Was it Edwin Hubble?
Edwin Hubble.
Very good. So,
Hubble.
yes, exactly. So this
Edwin
was
Hubble.
plotted by Edwin Hubble.
Edwin
So,
Hubble.
yes. So let me try to say what Edwin Hubble was looking into. So Edwin Hubble was looking into the spectrum of light that he was receiving. And what he saw that this is the usual spectrum we were expecting. But we see that these absorption lines, so in the spectrum, if there are other elements present or other molecules present in the background or in the foreground of the light that we are receiving, we will always get a absorption or an emission spectrum.
Yes, sir. We
So,
learned the Doppler's effect day before yesterday.
sorry?
The thing that makes these spectrums changes the Doppler's effect, right?
Yeah. So we are coming to that Doppler effect point. So these atoms and molecules emit lights, and as well as they sometimes absorb specific frequencies of light. So when they absorb these frequencies, we can see missing gaps in the spectrum. Usually the spectrum is very smooth, but occasionally the spectrum will have missing lines. Like for example, these black lines are the missing absorption spectra. But what we see is that these entire spectrum has shifted to the right side, which means it is shifted to the redder region. So if you look at this red, this absorption line is much closer to the transition region between here, or between these two lines, there is equal amount of yellow and red. But if you look at the spectrum that we receive here on Earth, it appears that it has moved towards the redder side, which means that the spectrum has red shifted. So this is exactly what the James Webb telescopes is also trying to do. So this is something called as redshift number. Z is the redshift. And as we move along the redshift from 10 to 11 to 12 to 13, we are having this Lyman break. Lyman break is a spectrum explicitly for the hydrogen lines. We can see that these lines are actually going to higher and higher wavelength. So it started somewhere here, but when we look at a higher redshift, it is going towards the right side. And if we go to even higher redshift, it is going further to the right side. And if we're going further to the redshift, it is going further to the right. So the spectrum looks almost identical, but the position of the spectrum has shifted. And that is how we know the redshift. And from the redshift, we can calculate the distance and also the velocities. So this velocity and distance has a correlation like this. If you are going further and further away, the velocity becomes higher and higher. Okay, and this was identified at a cosmological scale, and that is something what we call as the Hubble's law. Okay, so Hubble's law talks about the recessional velocity of the object is proportional to the distance, how far these objects are. And we understand the distance and the velocity based on the redshift. Okay. Usually the velocity can be determined from the redshift. The distance has to be determined in a different manner. But if you are able to calculate the distance, usually people use methods like parallax or a distance ladder method in order to calculate the distance. And once we have the distance, we see that the distance is proportional to the velocity, and the velocity is equal to some proportionality constants into the distance. And this proportionality constant is called the Hubble's constant. Usually, in the earlier time, we thought that this was a constant, but right now we understand that this is not a constant. This is more or less a parameter, and that is what we call as the Hubble parameter. Okay, so let me see. Animesh, Prakash, you have a question?
Sir,
Yes.
what is the Hubble constant and what does it mean?
Okay. So as you can see in this equation, the velocity of the object, for example, you are looking at a galaxy and this galaxy is moving away from us, which means that this galaxy has a velocity.
Yes.
Okay. And this velocity can be determined from the redshift, which we talked earlier. Okay. So this is the redshift, and that can be obtained from the shift in the spectrum. So from the shift in the spectrum, we can calculate what is the redshift. And from the redshift, we can calculate what is the velocity. And if you independently measure the distance, we see that the velocity of the object is proportional to the distance at which that object is. So
Yes.
whenever there is a proportionality, we can drop the proportionality by having a multiplicative constant there. And that constant is named as the Hubble constant. But right now we understand that this is not a constant, this is a
पहले देख
parameter.
रहा था
Okay. Sachi Aravind, you have a question?
Yes, sir. I had a few doubts, but I didn't get the third law of Kepler's planetary motion.
The third law of planetary motion.
Yes, I didn't get the law.
Okay, the first law states that the planets are going around in circular or not circular, elliptical orbit.
Elliptical orbits.
The second law states that the area swept by equal interval of time is equal. And the third law states that the square of the time period is proportional to the cube of the semi-major axis.
What is the time period?
Okay, time period is the time taken by the planet to go around the star once. For
Oh.
Earth, it is 1 year.
Hmm.
Okay, so if you take, for example, Moon and Earth system, the Moon goes around the Earth roughly in 27 days. Okay, so the time period is 27 days. And that
Yes.
is the T.
Okay.
Okay.
Yes. And
Okay.
also, why do different asteroids or comets have different orbits? Like some
Because
have.
they started out different. For example, we all have different ages, right? Because our starting point is different. I was born in 1990 something. You were born in 2000 something, which means that we had different initial condition. Like for example, different planet, different satellites, all thing has different initial condition, and they started out different at different time of the birth of the solar system. And that is the reason most of them have different mass and different orbital period, etc.
Okay, so good.
Sumeda, you have a question? I'm just reading the name in the screen. I'm not sure whether that is your name or parent's name.
Yes,
Uh,
yes, sir.
okay,
Sir,
what's your question?
sir, I didn't get the third. I didn't get the third Kepler's law.
Okay, the
The
third Kepler's law states that the time period, that is a T, and if you take the square of the time period, squaring means time period into time period. Okay, T square is T into T. Okay, and that is proportional to cube of the semi-major axis. Cube means you are multiplying it 3 times. Okay, if the A is the semi-major axis, A cube means A into A into A. Okay. Okay, we don't have to discuss too much of the Kepler's law because we have a few other things to discuss. Piyush Jana, you have a
Yes, sir.
question?
Sir, my question was that, sir, in school, sir, I have read what is velocity, but sir, here it is written recessional velocity, sir. So, what does that mean?
Okay, very good question. So recessional velocity means that the velocity at which they are going away from us. Okay, it may not be the actual velocity. Okay, for example, if you are traveling in a train and another train passes by, and it feels like that train is not too fast to us if we are both going in the same direction. Okay, so it's a relative velocity. And the recessional velocity is the velocity at which that particular object appears to be moving away from us. Okay, we don't know what is our velocity. We consider ourselves to be a fixed point, and from our fixed point, we are looking at them and we see them going away. Okay, at that velocity. And we call that velocity the recessional velocity. It is recessing away from us. Recessing means going away. Okay,
Okay, thank
Arnav,
you.
you have a question? You have raised your hand.
hello now sir.
Okay. Um, Akshasa Singh. I'm sorry if that is how you pronounce your name.
Sir, you pronounced my name Akshansh.
Okay, sorry. Akshansh. Very okay, nice. What's your question?
Sir, is the meaning of velocity and speed same?
Okay, they are slightly different because velocity takes into account of the displacement, while speed takes into account of the actual distance. Okay, they are slightly different, but if you are looking into straight line motion, they become same. Because if you're traveling in a straight line, the displacement and distance travel are the same.
This velocity is basically like displacement per second, and speed is distance per second.
Yes, exactly. Okay, I think I have uh, let everyone raise their hand. Okay, so now we can continue with our discussion. So this is the expression for Hubble parameter, and this is our Edwin Hubble looking through the telescope. It was a very hectic job that they did. Okay, Manasvi, you raised your hand. You have a question? Manasvi. Manasvi. I'm sorry if I'm pronouncing your name incorrectly. I'm very, very sorry. Manasvi. Okay, if you don't have any question, let me continue. So Hubble, we also know about Hubble Space Telescope. So using Hubble Space Telescope, we have taken much more detailed picture of our universe. So from these pictures, we see that it is not just planets, it is not just stars. It's a collection of whole stars all together, and each and every dot in this picture is actually a galaxy. Okay, so Hubble Space Telescope is an optical telescope kept in the outer space. So why do we want a telescope in the outer space? Can
So
anyone
can I
make a
answer?
guess?
So, I think that we need a telescope in outer space so that the much thing we can see from Earth, we can see more things from the outer space.
Sir, can I
So
answer?
that we can discover many galaxies like Andromeda galaxy.
Yes. I think
So that
most of
we can
you already
discover
know the
big
answer.
parts of the universe.
Yes. So we
So what?
started our discussion. I think most of you know the correct answer. Maybe we can lower your hands because I think everyone knows the correct answer to this question.
Yes.
Light
Uh,
pollution.
because if you kept a telescope under the atmosphere, we already know that there will be light pollution. And because of the light pollution, we can't get much more detailed images like this one. So if you kept a telescope outside in space, there is no atmosphere in space, right? It is well above our dense atmosphere, or we can say the atmosphere here is very rare, which means that this is going to have no disturbance of any kind of light pollution. Okay, whenever Hubble is facing outwards to the deeper and deeper sky, it can always collect light from the objects. Okay, so this is why we are interested in keeping a telescope outside the atmosphere. Other than Hubble, we have James Webb Telescope recently, which is doing the same thing, but in different wavelength regimes. Like in the case of IR and UV,
Sir,
Hubble was mostly optical, but James Webb is mostly IR.
sir, we had
Like
also
it's
Voyager 1 and Voyager 2 na, in our space, but they have
Sorry?
crossed. We had also Voyager 1 and Voyager 2 in the
Yeah,
space.
Voyager 1 and Voyager 2 are not space-based
telescope.
telescopes like Hubble and James Webb because Hubble is explicitly for optical observations and some UV and IR observations. But Voyager 1 and Voyager 2, they also took several pictures, but not as clean as this.
The
Yeah,
pale
sir,
blue
because
dot.
they were very old telescopes. Around they were launched in
Yeah, the
1970.
purpose of Voyager 1 and 2 are different. But in the case of Hubble and James Webb, they are very close to Earth, considered compared to Voyager 1 and Voyager 2. And the purpose of these telescopes are to stay in the orbit and to collect the data as we move on.
Okay, sir.
Okay, so
Thank
this
you.
is the Hubble Space Telescope, and you can see from these images that there is a unique signature of Hubble in these images. We will come to those points later, and that is this point. So if we take a Hubble Space Telescope observation and look at the image, we can see these four arms like this. But if you take the same optical image, but with the James Webb telescope, you will see 6 arms along with an extra arm that is perpendicular to the bigger one here. Okay, so that is based on the diffraction pattern of these satellites. Okay, so these are satellites. Why do we call them satellites? Because it is going around the Earth in particular orbits. And why do we call them telescopes? Because they are collecting light and making observations. So these are space-based telescopes. Okay, technically they are satellites, but much more interestingly, they are what we call as space-based telescopes. So with
So
James Webb,
as I
we can
as I can
have a
as I
better
can
picture
see,
of the universe.
yes.
So the universe picture, before that, let us see this video.
Ever since Edwin Hubble discovered that the universe is expanding, there's been a great debate about the speed of this expansion, also called the Hubble constant.
So we are going to discuss about the Hubble constant and its value. This is actual cosmology. This is what a cosmologist does.
But since then, two methods of calculating the expansion rate have gotten farther and farther apart. Some scientists think it's too big of a difference to just be a statistical. To calculate the Hubble constant, we need both a velocity and a distance. Velocities are easy. They require measuring the redshift of a galaxy as it recedes. But distances are much harder. We need standard candles, objects that shine with an intrinsic brightness. That way, its observed brightness.
So this is the problem that we had. So in the case of the Hubble's law, when we look at the Hubble's law, we can see that there are two inputs that we need. One is the velocity and the other is the distance. So velocity is something that we can calculate from the redshift, but distance is much harder to calculate. We need standard candles for that. And using the standard candle, we can actually make the measurement and
Sir.
see the value of it.
Sir,
Take a quick Hubble itself. Started by measuring distances nearby.
Yes.
sir, what are standard candles?
Yeah, we will discuss that after watching this video.
Okay.
Objects and working their way out. Hence the name, the cosmic distance ladder. The first rung within our Milky Way. Here we measure the distance in Cepheid, pulsating stars that have an intrinsic brightness. Then we look to nearby galaxies that contain both Cepheids and another type of standard candle, type 1a supernovae. These exploding white dwarf stars also have an intrinsic brightness. After calibrating these supernovae, astronomers then move out to a third rung, to even more distant galaxies that only contain supernovae. Linking all these measurements, a recent study has pinned the Hubble constant at 73. Instead of starting within our galaxy and looking out, the second method looks back in time to almost the beginning of the universe. Here we find the cosmic microwave background, the radiation left over from the Big Bang. The CMB's subtle variations in temperature describe changes in the density of the universe right after the Big Bang. Instead of standard candles, physicists use the size of the tiny fluctuations as standard yardsticks. With these yardsticks, they can calculate what the Hubble constant would be today. Recent estimates are at about 68, significantly lower than the cosmic distance ladder's approach. Both camps hope to resolve this debate in the coming years.
Okay. So this video tells a little bit more about the universe. So we come back to that video and the discussions in a moment. So the idea that we have is that if we are going away from each other, if we go back in time, there would have been a time we might be closer to each other. And if we go further back in time, there will be a time when we were much more closer. So if we keep on doing that, there will be a point when we all were at a one single point called as a singularity. So this is a problem. So we don't want singularities in our equations. We don't want singularities in the actual observations and all. So that is where the picture of the cosmos comes into. And that is what we call as the Big Bang
Sir,
picture. Yes.
sir, how do Cepheids and type 1a supernovas try? How do Cepheids and supernovas are used to measure the universe?
Okay, so I will come back to those points in a moment. The idea is that we need to measure the distance, how far they are. The Cepheid variables are kind of variable stars. By variable stars, it means that it has an intrinsic luminosity, but the luminosity changes. And the luminosity and the period has a particular connection. That means we know the intrinsic luminosity of Cepheid variables. And
Sir,
then
I
using basic parallax method, we can calculate the distance to Cepheid variables.
sir,
And then
and
we look for, let me complete. Then we look for galaxies with Cepheid variables and supernovae. And then we estimate the luminosity of the supernovae and we calculate the distance to that supernovae. Then using the distance luminosity correlation of the supernovae, we extrapolate a longer distance. So that is one way of estimating the Hubble parameter. And from what we understand is that the Hubble parameter in the earlier universe was bigger and is getting smaller and smaller and smaller these days, which means that the universe is expanding. But the problem is that if that is the case, if the universe is expanding towards the future, then there was a time when the universe was smaller in the past and we would reach a singular point. So in order to solve that singularity problem and every problem associated with that, people thought that, okay, there is a Big Bang. And after the Big Bang, there is a sudden expansion, which we call as the inflation. And after the inflation, there is a time called as the recombination, which is when the first light was emitted. And that light is what we call as the CMB, cosmic microwave background radiation. So when the CMB is emitted, there is no other stars or anything in order to illuminate the night sky. So we simply have a very dark age. And then after the dark age, there is a period of reionization. So during the reionization, the stars formed, and after the reionization, the stars start forming, and the stars collect towards forming galaxies, and the galaxies are formed in a very sequential way. So this is a prediction of the Big Bang model. The CMB is a prediction of the Big Bang model. So that is the cosmic microwave background radiation. And it was later discovered by Penzias and Wilson. It was an accidental discovery, but the actual observation, okay, let me skip that video. So we thought that there is a cosmic microwave coming from every direction in random noise kind of thing. So this was the first dedicated satellite for that, which is called as COBE. So COBE gave a picture like this. It is not very well resolved picture. Then we send the WMAP satellite, and WMAP satellite gave a much more detailed picture of the cosmic microwave background radiation, and we saw these fluctuations. And then we sent the Planck satellite, which was decommissioned very recently. And we still use the data from the Planck satellite in order to study the universe. And we see very sharp correlations. At some regions, it is very colder, some region it is very hot. These fluctuations in the cosmic microwave background radiation tells us about the structure of the universe. And the fact that this look almost homogeneous and isotropic tells a bit more about the universe, that the universe had a Big Bang expansion, or the beginning of the universe had a Big Bang, or maybe something closely related to the Big Bang. And then we had an inflation, and then followed by the reionization, or recombination, which emitted the CMB light. Okay, so this is one of the biggest predictions of the Big Bang model, and this was done by Penzias and Wilson. And this is a documentary video about that. I think I will probably skip that. And we saw the earlier structure of the universe was kind of like, there is like a wall kind of thing here. But with more and more detailed observation of the galaxies into farther and farther away in the universe, we see that there is no such detailed structure. It's a very kind of random picture that we have. And then we had the Solar Digital Sky Survey, from which we see that the universe is almost homogeneous and isotropic, which means it kind of looks the same in every direction. So the blue color is the actual data points, And the red color is the simulation that we do in the computers. And we see that they look almost identical. It's not exactly identical, but somewhat similar. So from which we understand that the physics that we know is reasonable to understand the universe. But one of the greatest observation comes from supernova. So supernovas are violent explosions in the universe, and we are particularly interested in things like type 1a supernova. So type 1a supernova, if there is a white dwarf, and white dwarf can accumulate mass from its surrounding. If the white dwarf becomes closer to something called as the Chandrasekhara limit, the Chandrasekhara limit is 1.4 times the solar mass. It will explode into a supernova. So that explosion is very particular. It always explodes at the Chandrasekhara limit. And based on that, we can say that it is at a particular distance. Okay, by measuring the luminosity, we can actually say how far this particular supernova is taking place. And from that, we can actually calculate the distance to the supernova. And from that, we can estimate the evolution of the universe. So by doing that, people were able to understand that the universe is not just expanding, the expansion rate of the universe is actually getting higher and higher. So the universe is accelerating. So this accelerated expansion of the universe is caused by something what we now call as the dark energy. Okay, so these are the people who discovered that. This is Rees, Perlmutter, and Schmidt. So if you look for the 1998 discovery of the expansion of the universe, you will definitely see the names of these people
मम्मी एक
who
काम
received.
करो
Sorry. So these people received the Nobel Prize for the discovery of the accelerated expansion of the universe. Okay, so what they understood is that the 73% of our universe is based of dark energy, something that we don't know. Then there is this 23% of dark matter. Then there is 4% of normal matter and 0.1 to 2% of neutrinos, and everything else comes in sub nominal levels. So what is dark matter and dark energy? So that is going to be the last part of this class. So when we look at the rotation of the galaxies, so galaxies, some of the galaxies have this rotation kind of feature. So these stars are going around a gigantic black hole at the center of our galaxy. Someone earlier already asked that the sun is also going around something, right? So that is a very good question. The answer to that question comes here. So sun is in our Milky Way galaxy, and most of the stars in the Milky Way galaxy is going around a black hole called as Sagittarius A star, which is at the center of our Milky Way galaxy, and many stars are violently going around it. So if we look at the velocity of stars at a very particular distance from the center of the galaxy, we see that it is keeping on increasing and increasing and increasing. But that is not what we expect. According to Newtonian mechanics or even general theory of relativity, we should be expecting a rise and then a drop in the velocity. But we are not seeing that drop. Instead of seeing that drop, we are seeing that these stars are going faster and faster, which means that there has to be some objects around there which is not visible to our naked eye. Okay, so we can observe the 21 centimeter hydrogen spectra and other starlights, and using these, we can actually calculate the velocity of these stars around a galaxy. And what we see is that, or what we understand from is that these galaxies are not slowing down. Okay, the velocities are getting higher, which means that there is some amount of matter which is not visible to our naked eyes. Or in another ways, there is a kind of matter which is not interacting with the light. So whenever there is a matter that is not interacting with the light, we call it the dark matter. Okay, so that is why it is called dark. Does not have any interaction with the fundamental interaction called as the electromagnetic interaction. And as a result, we call it the dark matter. Okay, so dark matter is this, but what is dark energy? So dark energy comprises of 73% of our universe, which is causing the universe to expand in an accelerated rate. Okay, so dark energy is different from dark matter. Dark matter is the cause which is much like the matter, but it is not emitting any kind of radiation. For example, star, quasar, supernova, all these are made of matter, but they can also emit light. But dark matter does not emit any kind of light. So if we
Does
have a
black
cosmological constant, which is a standard dark energy candidate, the
Sir, I
universe
have a
starts.
question.
Yes.
Does black holes come in the columns of dark matter? Black holes?
So there are theories in which black holes can act like dark matter, but in most of the case, we don't know what dark matter is.
As
So
you
we
said that
only
dark
have few
matter. Yes.
few more minutes left. We have to stop at 7 because there is another class at later time for other students. So let me finish the slides and then we will take questions. Okay.
Sir, can I leave? I have to go out somewhere.
Okay, you can leave at 7 if that is okay because we are at the very end of the classes here. Okay. So dark energy is something that causes the universe to accelerate its expansion. But usually there are different kinds of dark energy candidates. The simplest one is the cosmological constant, which is the famous cosmological constant by Einstein. And if the cosmological constant is there, the universe is going to expand forever. But there are other candidates. For example, there are possibility of quintessence-like or phantom-like dark energy. If the dark energy is very stronger than the cosmological constant, the universe is going to rip itself apart. So that is something what we call as the big rip. But if the dark energy is going to decay out, then it is going to be collapsing back. That is something what we call as the big crunch. And maybe the dark energy is going to decay out and we don't know what the future will be. So there are several candidates and the basic and the most simplest and the most prominent one is the cosmological constant. Cosmological constant is another name for the constant dark energy density. Okay. So how do we know all these things are there? Let me go to a better slide. So what you see is the Einstein's field equation at the very bottom. So this equation is the Einstein's field equation. So we started with Kepler's law. So Kepler's law are very basic laws about the motion of these things around another thing. But a detailed study says that that is not how things are moving. As someone already mentioned that the orbits can be complicated. So they comes into the picture because Newtonian mechanics is not relativistically consistent. In order to incorporate the ideas of special theory of relativity, we have to invent a different kind of gravity theory, and that is what we call as the general theory of relativity. And general theory of relativity has a few predictions. One is the bending of light, the other is gravitational waves. General theory of relativity also predicts the possibility of a cosmological constant. Okay, so this lambda you see here, this is the cosmological constant Einstein brought into the picture. Einstein thought it was a mistake, but later we realized that that is not a mistake. The cosmological constant is actually there. So this is can you make any guesses about these guys? This is Friedman and Lemaitre. So using Einstein's field equation, these two guys came up with the Friedman-Lemaitre model independently. So right now it is called as Friedman-Lemaitre-Robertson-Walker model or FLRW model. That is the standard model of the cosmology. And this is the expression connecting the Hubble parameter. So R dot by R is the Hubble parameter. And this is the energy density. This is the cosmological constant. And this is the curvature of the universe. If we set the curvature of the universe to 0, we get the standard Friedman equation. And that tells us when you compare it with the data, we get that there is a cosmological constant, and that constant is what is causing this dark energy kind of expansion. Okay, another prediction of the GR is the possibility of gravitational waves. when two objects are going around in a particular orbit. But as we go around, these orbits are no longer elliptical. They becomes a much more complicated orbit. And in the process, they also emit something what we call as the gravitational waves. Okay, so these gravitational wave emission takes place, and let's take that a bit slower. So these are all predictions from general theory of relativity. So general theory kind of tells us about how the universe is going to expand, and it also tells us about how things are behaving at smaller and smaller scales. So we started with simple elliptical orbit. Right now we have much more complicated orbit based on Einstein's field equations. So I think I completed most of the slides. So this is the Millennium simulation. So in the Millennium simulation, we can see that these is what our universe would look like at a very large scale. But when we go to smaller and smaller scales, we see this each point in this simulation is actually a galaxy. Okay, so this is how big our universe is. This is how complex and complicated our universe is. And to answer the question, what is cosmology? Cosmology is a scientific study of the universe as a whole. Its origin, structure, evolution, and ultimate fate. It seeks to understand the universe on largest scales, including its composition, dynamics, and laws governing its behavior. So if someone asks what is the cosmology, it is the understanding of the universe as a whole, or the study of the universe as a whole. We are not interested in what is happening inside the sun or what is happening inside a planet or a particular star. We are actually interested in how the whole galaxy is moving in this whole fabric of cosmos.